So this chapter is on bivariate analysis. Bi meaning two, variate for variable, so we're looking at things with two variables, and that makes a graph. And on a scatter diagram or a scatter plot, if you have a lot of plots of stuff, and here we have ages of husbands and wives, and generally it looks like, right, we don't have very many outliers. What are things that look the farthest away? This isn't even too bad, right? If we look at that one, he's 55, she's 62, so maybe 7 years difference. There's no crazy ones on here like, let's go there. Okay? What would that dot mean? She's 30, he's 80. What can you tell me about this? Is like an English class almost. You can make up your own story about the situation, right? Gold digger. Oh, wow, there we are. So there we got, right? So she's a gold digger. That's what you call that point. What do you call this point then? What? He's 30, she's 80. Cougar? Okay, all right. Having fun with data here. So now, how close the data, like in this situation, this data seems to have a relationship, okay? It seems quite likely that as the husband age increases, so does the wife's age. That most often they're related that way. It would be very weird to see human life go like this, okay, where it's the opposite. That would be a very interesting social experiment to do that. And we call that relationship between things a correlation. And sometimes there's a positive correlation and sometimes there's a negative one. This one in particular would be a positive correlation. So here are the three possible ones. Things are either positive, negative, or there's no correlation whatsoever. And within these, we'll talk about strong positive, weak positive, strong negative, weak negative. There's no strong zero or weak zero. It's just zero. So, how much money you make and how many years of experience. Generally, you'll make more money the more years of experience you have, so that would be something that's positive. And the dependent variable increases, so that's along your x-axis, the dependent variable, which is your y-axis, increases as your independent variable increases. Negative correlation is when you would have like a negative slope. So we've got temperature and elevation. As you go up higher, the annual temperature goes down. So that would be an example of a negative correlation. What does it say? I can't even read that on that last one. The day of the year and a draft number. I'm not even sure what they're trying to say with a draft number. Like military drafting, what number you get drafted as? It has nothing to do with what your birthday is. So you just get a scatter plot that's all over the place. And that would have no trend, zero correlation. So I want you to think about each of these situations. The best way to think about each of these situations, draw a little graph. So for the first one, distance from school and the amount of time it takes to walk here. Okay? So pick your independent variable and your dependent variable, independent along the x-axis, dependent along the y. Draw out a scatter plot and then determine what is that. That would be a positive correlation. So think about the other ones. Draw your graphs. and then we'll go over them. All right, we'll see how you did. There's a scatter plot for that one. No correlation. Gas in the tank is going to go down as the farther you travel. Teaching salary goes up. Starts up, if you're thinking of becoming a teacher, it starts going up really quick for 10 years and then it levels off. And then it just goes up a tiny bit. Mark earned and attendance in this class. Now this one I put a little bit all over the place because sometimes there's people that don't have to attend and do well. And sometimes there's people that attend every class and don't do well. There needs to be like a little bit of a, if you attend class but you don't listen or do anything while you're in the class, does it really count as attending class? I guess on the attendance sheet it does, but maybe not for helping you learn. So for drawing a scatter plot by hand, you're going to have to set up your graph. You're going to think about making sure you've labeled things clearly. A title, label your axes, label your variables, decide on an appropriate scale for your axes, and then plot all of the coordinates. If you have data that's in a column or in a row, it's always your independent variable that's listed first on your x-axis. Now I talked about before, there's more than just strong and, just more than just positive and negative. If the dots are all close to being a straight line, we would say that that is a strong positive correlation. If they still seem to be increasing but are more spread out, that would be a weak. And something in between you could call moderate. Same thing with negative correlations. And we're going to find out later that there's ways to measure the strength of how something correlates, if it's strong or not. A lot of times the graph that you make is linear, but there are times that the graph makes nonlinear relations. So here's one that kind of looks like an exponential or maybe a logarithmic graph. We saw in the tea cooling example of a scatter plot that made a negative exponential graph. So we have things that might appear to be something else. You might graph something and it turns out to look like a sinusoidal graph. Or if you throw a ball up in the air and measure its distance it travels, it might make a parabola. So I want you to take this, there's a graph given to you, figure out how you would set up your scale, how you would plot those points. Label everything neatly and correctly, and I'll walk around and give pointers on things that you might be missing. So that's what the scatter plot would look like there. Now a line of best fit, sometimes called a trend line, gives you an idea of what's happening with your data points. And when you draw that, you can see, oh, if my line's going up, then I know that it has a positive correlation. If my line's going down, I know that things have a negative correlation. And if you have a line of best fit, you can use it to make predictions. Just like we used a cumulative frequency graph to make predictions. You could look at this and say, well, according to this, if I put in 7 weeks of practice, I should get to about 70 words per minute. And you can use that data to make predictions about things within your data. You might have learned that's called interpolation, or even predict what would happen if I kept doing this, right? If I practiced for 5 years straight According to this graph, I'd be typing at probably 2,000 words per minute. Be awesome. They used to have typing. When I was in grade 7, we took typing classes. Do you ever have typing classes? And, oh, the typing classes, you would go through games, and it'd be like, can you go JJJ, KKK, JJJ, KKK, JJJ, KKK, JKJ, KJJ. Oh. Anyways, your fingers go back and forth like that, and they'd make you practice all of these different movements, and then you could type faster. So I took typing practice lessons when I was in grade 7. Oh, look at this. This is a nice trend line, the second graph. If you want to weigh nothing, you just keep running, right? Because it'll keep going down. So if you want to have a weight of 0, you just have to run like 300 kilometers a week, and you will be gone. Look at this one. There is one where someone, what do you think, that outlier there with the arrow, what's the story? Maybe he lied about how many, that could be true. People lie about certain things. Okay? Maybe that's an NFL football player. He runs that much per week but still weighs 250 pounds, and you don't want to run into him. So. Now, our line of best fit, we're going to figure out a number of different ways to find that line of best fit. And there is, obviously, when you're looking at your data, like here we have a line, that seems more realistic than this line. It seems more realistic than this line. How do we find out what is the best line of fit? What are strategies to draw that? Right? The second green line that I drew is bad, can you see, because there's more points above the line than below the line. So a line of best fit should have some points above and some points below to be accurate. Well, my first line that I sort of drew almost horizontal, it has some points above and some points below, but it also doesn't seem to capture what's happening with the increasing. So how do we draw a line of best fit that's best? Well, one way is to draw it by eye. And if you wanted to figure out by eye a place to start, you could figure out the mean point, or the average. Find the average of all your x values, find the average of all your y values, plot that point, and then still try to draw a line so through that point, so roughly half your points are above and half your points are below. So again, I'm going to get you to draw a scatter plot. I've got some of the work shown here, so you don't have to add up everything right now. But if we added up all of our x values, on average, I guess you're getting 22.3 grams of fat from a McDonald's meal. Well, this isn't, oh yeah, it must be McDonald's, Big Mac in there. And on average, you're getting 453 calories. So our mean point is 22.3 and 453. So on the graph below, put in all our data points and then draw a line of best fit through that mean point. So there's a scale that I chose. Again, I had a break in the graph there so that I could start with values that were closer. But if you started right at 0, this one wasn't too bad to go up to 600 and then go over to 34. And then if you label your mean point on your graph, and then draw your line of best fit. Now I'm going to take that line of best fit I don't know if it'll even, no, it's not going to allow me. It's going to just go orange. Maybe it looks like it should be slanted a little bit more. That way, but then this one's, yeah, might be a little bit. So again, you're eyeballing it a bit. We're not doing a perfect job of figuring this out. Of course, as a mathematician, as soon as someone is eyeballing something, someone else says there must be a best way. There must be a best way for us to figure this out so that we have it as small, as close to every point as possible. And the idea for doing that is very simple, very similar to the way we calculated variance by hand. Do you remember how we calculated variance by hand? We looked at how far away each score was from the mean, and then we squared it so that we were dealing with only positive values. So we're going to see a similar thing here. If we look at how far each of these points are away from our line, and we square all of those values, we want that number to be as small as possible. So as we move our line around, that value could change. So we have software that helps us figure out where the best line would be. Our calculator is going to do that for us, yes. So if we were finding the equation of our line of best fit or our regression equation on our own, well, oh yeah, these are just, we talked about these before, interpolation and extrapolation. But if we're finding that equation of a line to figure out stuff, we need to find that equation. Well, we're going to use our mean point, and then we're going to use another point that's on our graph so we can go back to our grade 10 math, y equals mx plus b, or y minus y1, mx minus x1. Use our slope point form or our slope-intercept form to find our equation of our line, and then we can use that to predict values. So here we have math marks. We've got our term mark and our final mark based on an exam, and there's one person that was absent for the exam. So that's been circled there in blue. Well, if we want to find the mean point for this data, then we have to ignore that person, because they don't have a value for their final score. So adding up all the scores and dividing by how many people you have gives you a mean point of 75 and 72. So for next class, you can start it right now if you want. Draw a scatter plot for this data. Plot your mean point. Draw a line of best fit and find the equation of that line. And then we're going to compare everybody's equations. So come prepared with your equation. Everybody's line will be slightly different. So you should have a different, if you do it on your own, you should have a different equation than somebody else, because you're going to, everybody's going to have the same mean point, but then you're going to pick one other point that's on your line. And chances are you're not going to pick the same point as somebody else to find your equation. So I want to see a whole plethora of equations so we can compare them.